Hello, welcome again. We are covering the topic Axial Flow Compressor for Civil Services Mains, IES and GATE Aerospace exam. And now we'll solve one question asked in Engineering Services 2010, that is, an axial flow compressor employed in the gas turbine plant delivers air at the rate of 300 kg per second and develops a total pressure ratio of 120. The inlet stabilization conditions are 300 Kelvin and 1 bar. The isentropic efficiency of the compressor is 87%. The compressor is having 18 stages and the blade speed is kept 200 meter per second to minimize noise generation. The stage degree of reaction at the mean blade height is 50%. The axial velocity of flow is 160 meter per second. The work done factor is 0.88. The hub tip diameter ratio is 0.8. Assume actual temperature rise in each stage. Instead of actual, equal should be there. Equal temperature rise in each stage. Take R is equal to 0.287 kilojoule per kilogram per degree Kelvin. Cp is equal to 1.005 kilojoule per kilogram per degree Kelvin. Work out the following. 1. Sketch the system, show the process on TS diagram and draw velocity diagram. 2. All fluid angles of first stage. And 3. The hub and tip diameter including blade. So these are the numerical questions. So here first we will draw the TS diagram. As there are 19 stages, so suppose this is your entry point and this is the exit point, and here the stagnation temperature is T01 and here the stagnation temperature is T01. Okay, so I will draw only this because it is difficult to draw 18 stages. So I will draw initial stage and final initial point and final point. Okay, and this is the condition if we carry out isentropic compression and the temperature reaches T019 dash. Okay. And it is given that the initial stagnation temperature is 300 Kelvin and pressure ratio is given as 20. So P019 by P01 is 20. So using isentropic relation, P019 by P01 is equal to P019 dash by P01. Read for gamma by gamma 1. We can find out T019 dash because we know that pressure ratio, we know that T01, so T019 dash comes out as 706.03 Kelvin. Okay. So this temperature is your 706.03 Kelvin, and isentropic efficiency is given, so we can find out T019 minus T01. So T019 dash minus T01 by isentropic efficiency is your actual temperature rise. So this is 706.03 and this is 300. So T019 minus T01 comes out as this quantity, and that is your 466.7. So this is your actual temperature rise. As it is given that the temperature rise in each stage is same, so in first stage or in first or in each stage it will be 466.7 by 18, so that will be 25.9. And as there is equal temperature rise, so work done in each stage will also be same. So work done per stage will be Cp into T02 minus T01, that will be 26.574 kilojoule per kg. As mass flow is also given, so we can multiply by mass also and find out the total work done in first stage. Okay. Now next is to draw the velocity diagram. So velocity diagram that we have drawn are the same. These are the velocity diagrams. This is inlet velocity diagram. This is the outlet velocity diagram. C1 is absolute velocity, V1 is relative velocity, U is blade velocity, CW1 and CA1 are component of C1. Similarly, this is an inlet, this is at outlet. C2 is absolute velocity at outlet, V2 is relative velocity at outlet, and these are this is blade speed, this is axial velocity. This is also axial velocity, and axial velocity is assumed same in both at inlet and outlet. So from velocity diagram, CW2 is equal to CA tangent alpha 2, and CW1 is equal to CA tangent alpha 1. Okay. CA1 and CA2 are same. So from these diagrams we can CW1 is the CA tangent alpha 1 and CW2 is the CA tangent alpha 2. So now work done is U CW2 minus CW1 into lambda. Lambda is the work done vector, and we can put CW2 in terms of CW2 and CW1 like this in terms of C and alpha 2 and alpha 1. Okay, and for 50% degree of reaction, alpha 2 is equal to beta 1 and alpha 1 is equal to beta 2. So this can also explain like this. Now blade velocity is given, that is 200 meter per second. Axial flow velocity is given, CA is given, that is 160 meter per second, and lambda is given. So we can find out the work done. Okay, in terms of tangent alpha 2 and alpha 1, and that work done we have already found out, that is 26.05 kilojoule per kg. So converting into joule, we can find out tangent alpha 2 minus tangent alpha 1. So tangent alpha 2 minus tangent alpha 1 comes out as 1.0178, and from velocity diagram, U by CA is equal to tangent alpha 1 plus tangent beta 1. Okay, U by CA is equal to tangent alpha 1 plus tangent beta 1, and for 50% degree of reaction, this beta 1 is equal to alpha 2 and alpha 1 is equal to beta 2. So converting this alpha 2 or converting this beta 1 into alpha 2, so it will be tangent alpha 2 plus tangent alpha 1 is equal to 1.25. So from this third and from 6 we can solve it for alpha 2 and alpha 1. So alpha 2 comes out as 48.59, that is equal to beta 1, and alpha 1 comes out 6.62, that is equal to beta 2. Now mass flow rate is given, that is 300 meter per second, 300 kilogram per second. So dp is your tip diameter and dh is half diameter, and then the mass flow rate is m into pi by 4 dp square by dh square into 3 into density, but density is not known. So now we'll find out density. To find out density, we'll find out C1 first, inlet velocity. Now CA is known, alpha 1 is known, so CA is 150 and alpha 1 is 6.62, so C1 comes out as 161.0 meter per second. From this C1, dynamic temperature at inlet can be calculated, that is C1 square by 2 T2, and if we subtract from the stabilization temperature, we can find out P1, so that is 287.092. So now using isentropic relation, we can find out static pressure also. P1 by P01 is equal to P1 by T01 divided by gamma by gamma. So that is 287.092, and this is 300, and this is 3.5, this value, and P01 is 1 bar, so P1 comes as 0.857 10 per 5 Newton per meter square. And using state equation, we can find out density, that is 1.0405 kilogram per meter square. Now we can put here in this equation that in this equation, the value of CA, DA, DP, dP by dH is 0.8. So from this we can find out dP, that is 2.525 meter, and dH comes out as 2.020. So these are the